I expected to integrate this question, integral dx over 1 positive x squared. I know that I can easily use the perfect square formula to rewrite this as x positive 1 over 2 whole squared. If I were to expand, I get x squared positive 2 times x times 1 over 2, that's going to give me x positive 1 over 2 whole squared, that's 1 over 4. If I were to add 3 over 4, that in turn would give me this 1. Now I can rewrite this as integral dx over x positive 1 over 2 whole squared positive root of 3 over 2 whole squared. This is similar to integral dx over x squared positive a squared, which has a formula 1 over a tan inverse of x over a positive arbitrary constant c. Okay, so if you were to apply this, you get 1 over root of 3 over 2 tan inverse of x positive 1 over 2 divided by a root of 3 over 2. This can be further rewritten as 2 over root 3 times tan inverse of, you take the LCM, you get 2x positive 1 divided by 2 multiplied with 2 over root 3. Now 2 gets cancelled, giving me 2 over root 3 tan inverse of 2x positive 1 divided by root 3. So this is what we have got as a solution. Okay, now this is simple. You don't have to use much of the mathematical computation ability to arrive at the solution. Now let us consider the denominator, which is 1 positive x squared. Now this is similar to the geometric series expansion, which is given as a positive ar squared, etc. positive a times r raised to the power of n, which can be rewritten as a times of 1 negative r raised to the power of n divided by 1 negative r, where a is equal to 1 and my r is equal to x in this case, and find out the number of terms. You got 1, 2, 3, so n is equal to 3. So if I were to utilize the following values over here, then this would be rewritten as 1 positive x squared is equal to a is 1 times 1 negative r is x. How many terms are there? 1, 2, 3. 3 terms are there. So substitute that 3 divided by 1 negative x. So this can be further rewritten as 1 negative x cubed divided by 1 negative x. So therefore integral dx over 1 positive x squared is rewritten as dx over 1 negative x cubed divided by 1 negative x. You can flip this, you get 1 negative x over 1 negative x cubed multiplied with dx. This can be further rewritten as dx over 1 negative x cubed negative x times dx over 1 negative x cubed. Now what I'm going to do is I'm going to consider this exclusively and I will be solving it. Now by linearity I would like to rewrite this as dx over negative of x cubed negative 1, which is equal to negative integral dx over x to the power of 3 negative 1. Now I would consider exclusively dx over x to the power of 3 negative 1. Now we know that a cubed negative b cubed is a negative b multiplied with a squared plus ab plus b squared. In this case I have x cubed negative 1, so a is equal to x and b is equal to 1. Substitute that. This is going to be x negative 1 times x squared times x into 1 positive 1. So you take this and you substitute it here. So this is equal to integral dx over x negative 1 times x squared plus x plus 1. I would now consider 1 over x negative 1 times x squared positive 1. So I'll rewrite this as a over x negative 1 and bx positive c over, because the degree is 2, x squared positive 1. You cross multiply, you get a times x squared positive 1. This is bx positive c times x negative 1. I take x is equal to 1. This will become 0. 1 and 1, 2 and 3. So this is 3 times a. And on the left you got 1. So 1 is equal to 3 times a. Therefore a is equal to 1 over 3. Now next I would like to take x is equal to 0. This will be 0, this will be 0, so you get 1 is equal to a. This is going to be 0 and you get c times of negative 1. So this is going to be a negative c, but a is 1 over 3, and you can rewrite negative c is equal to 1 negative 1 over 3. Negative c is equal to 3 negative 1 over 3, which is 2 over 3. Since you have a negative here, push the negative to the other side, you get c is equal to negative 2 over 3. Now you got a and you got c, you need to get the value for b. So I will just take a random value, let x is equal to 1. So that means if you substitute it here, you get 1 1 1. So 3 times a plus b positive c. Now if you were to substitute, we have already taken a x is equal to 1, so I will just change it to x is equal to negative 1. So if I were to take x is equal to negative 1, this is going to be 1, negative 1 positive 1 gets cancelled, so I get a, so 1 is equal to a, positive, b is going to be with the negative sign because x is equal to negative 1, and positive c, negative 1, so it's going to be negative 1 negative 1, so negative 2. I know the value of a, 1 over 3, and the value of c is going to be negative 2 over 3, and you got a negative 2. Just to distribute that, negative 2, you get positive 2 times b, you got positive 4 over 3. You add these two together, you would get 5 over 3 positive 2b. You got a 1 there, so I'm just placing the 1. So 2b is equal to 1 negative 5 over 3. So this is 3 negative 5 over 3 is negative 2 over 3. So this 2 and this 2 gets cancelled. So b is equal to negative 1 over 3. So let me move on to the next sheet of paper. And I got the value for a, b, c. So a is 1 over 3. So therefore 1 over x negative 1 times x squared positive 1 will be equal to 1 over 3. So let me write that in this fashion. And b is negative 1 over 3. So negative 1 over 3 times x divided by x squared positive 1, and c is negative 2 over 3. So negative 2 over 3 x squared positive 1. Okay, so we need to integrate this quantity. So the integral of this is going to be equal to integral 1 over 3 dx over x negative 1, negative 1 over 3 x times dx over x squared positive 1, and then negative 2 over 3 integral dx over x squared positive 1. So this is what we have got, and we can integrate this. Now these two can easily be integrated, but for this let me just consider integral x dx divided by x squared positive 1. Now I got x squared positive 1, so what I'm going to do is I'm going to multiply by 2, and I'm going to add a 1, and I'm going to take away 1 in the numerator, right? So this is going to be the case here. Now adding 1 and removing 1, it's not going to harm us, but this product multiplying the value of x with the 2 has to be countered. So I'm going to divide by 2, and this is going to be x squared positive 1 multiplied with dx. So this can be further rewritten as 1 over 2 times integral, distribute this 2x positive 1, right? 2x positive 1 times dx divided by x squared positive 1, and then distribute this with the negative dx divided by x squared positive 1. Okay, so you have a quantity like this. So what have I done? Instead of this is going to be the quantity that I will represent, or use. So let me take this as 2. Therefore I can rewrite 2 as, instead of this I would push in this. So this is going to be equal to 1 over 3 integral dx over x negative 1. There is a 1 over 3 there. And as I mentioned to you, in place of this you put this. So you have 1 over 2 integral 2x plus 1 times dx divided by x squared positive x positive 1, and then negative 1 over 2 times negative dx. So it's going to be negative 1 over 2 integral dx divided by x squared positive x positive 1, and then you have this quantity. So that's going to be negative 2 over 3 integral dx over x squared positive x positive 1. Now I will distribute 1 over 3. So this is going to be 1 over 3 integral dx over x negative 1. Negative 1 over 3 times 2 is 6 integral 2x positive 1 divided by x squared positive x positive 1 times dx. Negative negative positive, you have 1 over 3 times 2. I will tell you why I am doing it so. So dx divided by x squared positive x positive 1, and you got negative 2 over 3 integral dx over x squared positive x positive 1. Now this can be handled, this can be handled. Now for this I will take 1 over 3 out. If I were to take 1 over 3 out, this is going to be 1 over 2 times integral dx over x squared positive x positive 1, and this is going to be 2 times, right? 1 over 3 is out, 2 times integral dx over x squared positive x positive 1. Now if I were to simplify this, this is going to be 1 over 2 negative 2, which is going to be 4 minus 1, 1 negative 4 divided by 2, that's going to be negative 3 over 2. This is going to be the summation of these two integrals. So just for being consistent, I'm going to rewrite this 1 over 3 integral dx over x negative 1, negative 1 over 6 integral 2x plus 1 times the dx divided by x squared positive x positive 1. Now this is summed up as positive 1 over 3 times, you have negative 3 over 2. Probably you can just simply place the negative 3 over 2, and you have dx divided by x squared positive x positive 1. Now 3 and 3 gets cancelled, and this is nothing but 1 over 3 integral dx over x negative 1, negative 1 over 6 integral 2x plus 1 times dx divided by x squared positive x positive 1. This is going to be negative 1 over 2 integral dx over x squared positive x positive 1, and we can now give the integration for all these terms. Okay, so let me go to the new side of the page and show you the outcome. Okay, so probably I need to, okay, I've got this. Now this can be actually obtained as follows. So I'm just going to consider integral 2x plus 1 times dx divided by x squared positive x positive 1. So let x squared positive x positive 1 be equal to sum t. This is 2 times x positive 1 times dx is equal to dt. Substitute that, is going to be integral dt over t, which is nothing but ln of t, which is equal to ln of x squared positive x positive 1. Okay, so you got this integration. This is already done. Now next you consider integral dx over x negative 1, which is nothing but ln of x negative 1, right? Because if you had to substitute x negative 1 is equal to sum t, this is dx is equal to dt, and you have dt divided by t, which is equal to ln t, which is nothing but ln of modulus x negative 1 plus arbitrary constant c. So number 2 is done. Now 1 is done, 2 is done. Number 3, This is number 3, right? So just go there. Now let me take this as 3. So you consider integral dx over x squared positive x positive 1. I would like to write this as integral dx over x positive 1 raised to the power of 2. You get x squared positive 2x, right? I don't want a 2x, I want x, so I divide this by 2. So 2 times x times 1 over 2, that will give me x positive 1 over 2. Now 1 over 2 squared, that's going to be 1 over 4, but I need a 1 over 4 added with 3 over 4, right? So this is equal to integral dx over x positive 1 over 2 whole squared positive root of 3 over 2 whole squared. Now this is similar to integral dx over x squared positive a squared, which is nothing but 1 over a tan inverse of x over a. So utilizing this is going to be 1 over a is this times tan inverse of x over a. A is this. So you have to rewrite this. This is 2 over root 3 tan inverse of 2x positive 1 divided by 2. You flip this, you get 2 over root 3, and then 2 gets cancelled. So this is going to be 2 over root 3 tan inverse of 2x positive 1 divided by root 3 plus c. So this is what you've got. So I can rewrite 3 in the following fashion. So let me write that. So therefore 3 is rewritten as 1 over 3 is over here, 1 over 3 is over here. So just start with 1 over 3 and then integral dx over x minus 1, that's ln modulus x negative 1, that's fine. Next you got negative 1 over 6, negative 1 over 6, and what is that you got? You got ln of x squared positive x positive 1. So ln of x squared positive x positive 1, so that is done. And the last one is negative 1 over 2, negative 1 over 2, and what have you got? You got 2 times root of 3 tan inverse of 2x positive 1 divided by root of 3. Now 2 are cancelled, giving me 1 over 3 ln modulus of x negative 1, negative 1 over 6 ln of x squared positive x positive 1, negative 1 over root 3 tan inverse of 2x positive 1 divided by root 3. So this is what we have got. And what is this? This is 3. And why did we get all these values of 3? Because we started with this, and now this is going to be represented with the output. But what exactly is this? Let me show you. What exactly is this? Now this has been considered, but this is nothing but this, right? But what is this? This is nothing but this, okay? But we just took off like this, but there is a negative sign over here. So to write the final answer, we should pre-multiply every quantity with negative sign. So therefore negative integral dx divided by x cubed negative 1 is equal to, you got to multiply everything by negative sign. So I start with this term, it's going to be 1 over 6, it's going to be positive ln modulus x squared positive x positive 1, and this is going to be negative 1 over 3 ln modulus x negative 1, this is positive 1 over root 3 tan inverse of 2x positive 1 over root 3 positive arbitrary constant c. Okay, so we have reached here and I have shown you how to integrate this. Now what I'm going to do is I'm going to be showing you how to integrate this particular quantity. So for that, let me go to a new page. Consider integral x over 1 negative x cubed times the dx. Now by linearity I can rewrite this as x over negative of x cubed negative 1 times dx, which is again rewritten as negative x over x cubed negative 1 times dx. Now let me exclusively consider integral x over x cubed negative 1 times dx. Now there is a formula which is a cubed negative b cubed, and it is written as a negative b times a squared plus ab plus b squared. So by this formula, x cubed negative 1 cubed, it doesn't matter whether you write 1 or 1 cubed, it means the same. It's going to be x negative 1 times x squared positive x into 1 is x positive 1. So therefore, if I were to take this as sum 1, or let me take it as 2. So therefore, I can rewrite 2 as, in place of x cubed negative 1, I'm going to have x negative 1 times x squared positive x positive 1. The numerator has got an x, and that is multiplied with dx. Now, let me now consider x over x negative 1 times x squared positive x positive 1. I'm going to utilize partial fractions. So a over x negative 1, since the degree is 2, this is rewritten as bx positive c divided by x squared positive x positive 1. So we cross multiply, I get a times x squared positive x positive 1 positive bx positive c times x negative 1. On the left I get x. Now I will first allow x is equal to 1, so this will become 0. Now this is going to be a of 1 positive 1 positive 1, which is equal to 3 times a. On the left I got a 1, so therefore this is going to be 1 over 3. So that's a value for a. Next, let me just take x to be equal to 0. Okay, so this term, if I were to substitute x is equal to 0, this goes off, this goes off, so I get a negative c. This goes off, this goes off, so I get a x is equal to 0, this goes off. So therefore a is equal to c, which means the value of c is also equal to 1 over 3. So now I've got a, I got a c. Let me choose a random value, say x is equal to negative 1. If I were to substitute x is equal to negative 1, I get a positive 1 here, a negative 1 and a positive 1. So I get a here. If I were to choose negative 1, that's going to be negative b, positive c, negative 1 is going to be negative 2. So this is equal to a, distribute 2, you get 2 times b, negative 2 times c. Now a is 1 over 3 and c is 1 over 3, so that's going to be negative 2 over 3, positive 2 times b. Now we have taken x is equal to negative 1, so on the left you have a negative 1, negative 1. Now you add these two things and you will get negative 1 over 3, positive 2 times b. You have a negative 1. Push this to the other side, you get negative 1, positive 1 over 3 is equal to 2 times b. This is negative 3, positive 1 over 3, which is negative 2 over 3 is equal to 2 times b. 2 gets cancelled. Therefore the value of b, let me write that down, b is equal to negative 1 over 3. Okay, so I will substitute a value, b value, c value. Let me utilize this part of the paper. So therefore if I were to take this as sum 3, therefore 3 is rewritten as x over x negative 1 times x squared positive x positive 1. A is 1 over 3, so 1 over 3 times x negative 1. B is negative 1 over 3 times x divided by x squared positive x positive 1, and c is 1 over 3. Right, that's exactly what we have got, 1 over 3 and 1 over 3, and b is negative 1 over 3. So now what I would do is I would just split these things, right? Our ultimate aim is to integrate, right? So I've taken this to be as say 2 dash. So therefore I can rewrite 2 dash as, therefore 2 dash is rewritten as, so this is going to be integral. In place of this, I'm going to substitute this. So it's going to be 1 over 3 times dx over x negative 1, negative 1 over 3 times x dx divided by x squared positive x positive 1, and 1 over 3 times the integral dx over x squared positive x positive 1. Okay, so this is equal to 1 over 3. Now this is easily integrable, right? X negative 1. Now for this, what I wish to do is I would like to multiply by 2 and add a 1 and a subtract 1, because when I differentiate x squared positive x positive 1, I will get a 2x positive 1. So to counter that, I am writing the numerator in this fashion, divided by x squared positive x positive 1. But since I multiplied by 2 and these two terms add up to 0, all I need to do is counter that with a product multiple of the denominator with 2. So this is followed by 1 over 3 integral dx over x squared positive x positive 1. So this is what we have got. Now this can be rewritten as integral. I'm not integrating this, I know the value, but let us be consistent. So this is going to be negative 1 over 6 times. I will split this as 2x positive 1 times dx. So dx is there, divided by x squared positive x positive 1. Now this quantity of 6 will be following this 1 also, right, with negative 1. So that is going to be giving us negative negative positive. So positive 1 over 6 integral dx over x squared positive x positive 1, and you have a positive 1 over 3 integral dx over x squared positive x positive 1. Okay, so fair enough. This is what we have got. What I can do is I can add up these two things. If I add up these two things, it's going to be 1 over 6 and 1 over 3. I take the LCM as 6, I would get 1 positive 2, which is 3 over 6 is going to be 1 over 2. So these two can be clumped, and I get 1 over 3 integral dx over x negative 1, negative 1 over 6 integral 2x positive 1 times dx divided by x squared positive x positive 1, positive 1 over 2 times integral dx over x squared positive x positive 1. Okay, now if I were to consider this, let me just consider integral 2x positive 1 divided by x squared positive x positive 1 times dx. Let me take x squared positive x positive 1 is equal to sum t. I differentiate, I get 2x positive 1 times dx is equal to dt. So that is there in the numerator. So this is going to be dt divided by t. You integrate this, you get ln of t, which is nothing but ln of x squared positive x positive 1. You don't have to add the arbitrary constant because it's only part of this quantity. So this is done. Now let me consider this one. Consider integral dx over x squared positive x positive 1. I want to rewrite this as integral dx over x positive 1 over 2 whole squared. You expand this, you get x squared positive 2 times x times 1 over 2 is going to be x, and you have 1 over 4. But if I were to add 3 over 4, 1 over 4 added with 3 over 4 will give me 1. This can be further rewritten as dx over x positive 1 over 2 whole squared positive root of 3 over 2 whole squared. This is similar to integral dx over x squared positive a squared, which is equal to 1 over a tan inverse of x over a positive c. Now let me go to the next sheet, and thereby I can rewrite this as 1 over, this is a, so the root of 3 over 2 tan inverse of x positive 1 over 2 divided by root 3 over 2 tan inverse of x over a. So this can be further rewritten as 2 over root 3 tan inverse of 2x positive 1 divided by 2 multiplied with 2 over root 3. 2 gets cancelled, giving me 2 over root 3 tan inverse of 2x negative, it's positive 1, right? So tan inverse, so 2x positive 1 divided by root 3. So this is the term for this. We just considered this. So if I were to unify everything, if I were to take this as sum 3 dash, so I can rewrite this, right? So therefore the 3 dash, therefore 3 dash is rewritten. This is going to be 1 over 3 times ln modulus of x negative 1. So this is the quantity, followed by negative 1 over 6. This quantity is this. So it's going to be ln modulus of x squared positive x positive 1, and this quantity is going to be this. So positive 1 over 2 times 2 over root 3 tan inverse of 2x positive 1 divided by root 3. 2 gets cancelled. So if I were to rewrite this, this is 1 over 3 ln modulus x negative 1 negative 1 over 6 ln modulus x squared positive x positive 1 positive 1 over root 3 tan inverse of 2x positive 1 divided by root 3. But what is all of this? This is what we have got, and actually we are splitting this term, but where did we get that? I need to show you where exactly we got that. So let me move up and show you that. So this is the term. You see that we split it in partial fractions and we integrated and we got it, but apparently this is what we considered, but this is what we require, right? This is the requirement. So therefore what I will do, therefore integral, I'm going to write this. What is it? Negative x over 1 negative x cubed. This is x cubed negative dx. This is x cubed. So therefore integral with a negative sign x over x cubed negative 1 times dx. This is what is this without the negative sign. So now I will bring in the negative sign. If I were to bring in this negative sign, I would have a pre-multiplying with this quantity, right, with the negative 1 over x. That's going to be positive 6 times ln modulus x squared positive x positive 1. This is going to be negative 1 over 3 ln modulus x negative 1, and this is going to be negative 1 over root 3 tan inverse of 2x positive 1 divided by root 3. So this is this with the arbitrary constancy x over 1 negative x cubed times dx, which is apparently this representation. So because it allowed us to utilize the all important formula of a cubed negative b cubed. Now if you were to remember, we have already worked out this solution, right? Okay, we know that integral dx over 1 negative x cubed is equal to 1 over 6 times ln modulus x squared positive x positive 1 followed by negative 1 over 3 ln modulus x negative 1 positive 1 over root 3 tan inverse of 2x positive 1 divided by root 3, right? This is the value that we got for this, and also we have obtained a value for x dx over 1 negative x cubed. And what is that value? It's 1 over 6 ln modulus x squared positive x positive 1 negative 1 over 3 ln modulus x negative 1, and then negative 1 over root 3 tan inverse of 2x positive 1 divided by root 3. So we will take in this value, place it here, take in this value, place it here. So if I were to take this as sum 4, I can rewrite it here. So therefore 4 is rewritten as, right in the first term, it's going to be 1 over 6 ln modulus x squared positive x positive 1 negative 1 over 3 ln modulus x negative 1 positive 1 over root 3 tan inverse of 2x positive 1 divided by root 3. You have a negative sign going here, so every quantity has to be pre-multiplied with negative. So it's going to be negative 1 over 6 ln modulus x squared positive x positive 1 negative negative positive 1 over 3 ln modulus x negative 1 negative negative positive 1 over root 3 tan inverse of 2x positive 1 divided by root 3. Okay, now negative 1 over 6 ln of x squared positive x positive 1 will get cancelled with 1 over 6 ln of x squared positive x positive 1. So similarly these two gets cancelled. Now what you got 1 over root 3 and 1 over root 3. 1 over root 3 tan inverse of 2x positive 1 over root 3. These two can be added. So if you were to add these two things, what you are going to get? You are going to be getting a value of 2 over root 3 tan inverse of 2x positive 1 divided by root 3 positive arbitrary constancy, because it's indefinite. These integrals are indefinite integrals, Now, if you were to focus, so this is the solution. This is a solution. This solution has been obtained exclusively by applying the geometric series. Now, I want to show you the result that we got by applying the formula. Now, if you remember, I just applied the formula for this question, and this is the formula that was applied. And what did I get? I get 2 over root 3 tan inverse of 2x positive 1 divided by root 3. And what did I get here? 2 over root 3 tan inverse of 2x positive 1 divided by root 3. So this is a lovely way of actually applying different concepts that we have learned in algebra. This is actually an algebraic property, right? But we have utilized the algebraic property to solve an integral question. So that will broaden your horizon of computational mathematics. Thank you, everybody. Enjoy your life.